Wherever you find yourself right now, whether you're settling in for the evening or just starting your morning, I'm genuinely glad you're here with me. Tonight we're diving into something that will completely change how you think about one of the most fundamental constants in our universe. We're exploring why, despite centuries of scientific advancement and billions of dollars spent on precision instruments, no one has actually measured the speed of light. What I'm about to share with you isn't some fringe idea from the depths of the internet. It's a profound truth that sits at the very heart of modern physics, acknowledged by every major scientific institution on Earth, yet somehow remains hidden from most people's understanding of how science actually works. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Let's start. Now, let me ask you something that might sound simple at first. When was the last time you measured something? Maybe you checked your height, weighed yourself, or used a ruler to measure a piece of furniture. We measure things constantly in our daily lives, and we take it for granted that measurement is straightforward. You take your measuring device, you compare it to the thing you want to measure, and you get a number. But what if I told you that the most important speed in the entire universe, the cosmic speed limit that governs everything from the light reaching your eyes right now to the fundamental structure of space and time itself, has never actually been measured? What if I told you that it's impossible to measure it, not because our instruments aren't good enough, but because of something far more profound about the nature of reality itself? This isn't a story about scientific failure or technological limitations. This is a story about one of the most elegant and mind-bending revelations in all of physics. A revelation that shows us how the universe is far more interconnected and mysterious than we ever imagined. The speed of light is everywhere in physics. It appears in Einstein's famous equation. It determines how fast information can travel through the universe. It shapes the structure of atoms, and it even governs the expansion of the cosmos itself. We know this speed to incredible precision. We can tell you that light travels at exactly 299,792,458 meters per second in a vacuum. Not approximately that speed, but exactly that speed, defined to the very last digit. But here's the thing that will blow your mind. That number isn't the result of a measurement. It's a definition. It's been written into the laws of physics by human decree, not discovered through experimentation. And the reason why reveals something so fundamental about the nature of reality that it changes everything we thought we knew about measurement, space, time, and the very fabric of existence itself. Let me paint you a picture of what this means. Imagine you're trying to measure how fast your friend can run. Simple enough, right? You need two things: a way to measure distance and a way to measure time. You mark out 100 meters with a measuring tape. Start your stopwatch when your friend begins running. Stop it when they cross the finish line and divide distance by time to get their speed. But now imagine trying to measure the speed of light using this same approach. You'd need to measure the distance light travels and the time it takes to travel that distance. Sounds straightforward, but there's a catch that cuts to the very heart of what measurement actually means. To measure distance, you need a ruler. But what makes a ruler work? What ensures that the meter marks on your ruler are actually 1 meter apart? In the modern world, we define the meter using specifically A, the speed of light. Meter is defined as the distance light travels in 1/299,792,458 of a second in a vacuum. Do you see the problem? We're trying to measure the speed of light, but our definition of distance depends on the speed of light. We're stuck in a logical circle where we'd need to know the answer before we could measure it. But it gets even stranger when we consider time. To measure how long light takes to travel a certain distance, we need a clock. But what makes a clock tick at the right rate? Modern atomic clocks work by counting the vibrations of atoms, but those vibrations are electromagnetic phenomena that propagate at, you guessed it, the speed of light. So here we are, trying to measure the speed of light using rulers that are defined by the speed of light and clocks that depend on the speed of light. It's like trying to measure your own height using a ruler that changes length based on how tall you are. This isn't just a technical problem that we might solve with better instruments or cleverer techniques. It's a fundamental feature of how the universe works, revealing something profound about the relationship between space, time, and the speed of light itself. The story of how we got to this point is absolutely fascinating, filled with brilliant minds, ingenious experiments, and gradual realizations that forced us to completely reimagine our understanding of reality. For over 2 centuries, physicists tried their best to measure the speed of light, and they got remarkably close to what we now call the correct value. But each time they thought they had measured it, they were actually doing something subtly different. They were calibrating their instruments, comparing different physical phenomena, and establishing relationships between various constants of nature. What they thought was measurement was actually a complex dance of definitions and assumptions about the fundamental structure of reality. The breakthrough came when physicists realized that the speed of light isn't just another physical property like the mass of an electron or the charge of a proton. It's something far more fundamental. It's the conversion factor between space and time, the cosmic exchange rate that tells us how much distance equals how much duration in the universe's bookkeeping system. Einstein showed us that space and time aren't separate things that exist independently. They're woven together into a single fabric called space-time, and the speed of light is essentially the speed of space-time itself. It's the maximum rate at which cause and effect can propagate through the universe, the ultimate speed limit that governs everything from quantum particles to cosmic expansion. When you understand this, you realize that asking for the speed of light to be measured is a bit like asking someone to measure how many inches are in a foot. The answer isn't discovered through experimentation, it's established by definition. We decide that there are 12 inches in a foot, and that decision becomes part of the framework we use to measure everything else. Similarly, we've decided that the speed of light is exactly 299,792,458 meters per second, and that decision has become part of the framework we use to measure space and time themselves. This isn't arbitrary. It's based on centuries of careful experimentation and theoretical development. But it's still fundamentally a choice about how we want to organize our understanding of the universe. This revelation opens up profound questions about the nature of scientific knowledge itself. What does it mean to measure something? How do we distinguish between discovery and definition? What aspects of reality are objective features of the universe, and what aspects are human constructs that we impose to make sense of our observations? The speed of light sits at the intersection of these deep philosophical questions and the practical needs of modern physics. It's simultaneously the most precisely known constant in all of science, and something that has never been measured in the traditional sense of the word. But this isn't the end of the story. It's actually just the beginning of a journey that will take us into the heart of how modern physics actually works, how we define the fundamental units that govern everything from GPS satellites to particle accelerators, and why the impossibility of measuring the speed of light reveals something beautiful about the elegant mathematical structure underlying all of reality. In the next part of our exploration, we'll dive deeper into the historical attempts to measure light speed, the ingenious experiments that brought us closer and closer to understanding its true nature, and the moment when physicists realized they had been asking the wrong question all along. We'll discover how this apparent limitation in measurement actually opened the door to our modern understanding of space, time, and the fundamental constants that govern the cosmos. We'll explore how this seeming impossibility actually led to one of the most beautiful unifications in all of physics, connecting the smallest quantum scales to the largest cosmic structures through a single elegant principle. But before we dive into those historical adventures, let me share something that will help you appreciate just how extraordinary this situation really is. Think about every other fundamental measurement in physics. When we want to know the mass of an electron, we design experiments to measure it. When we want to determine the strength of Earth's gravitational field, we drop objects and time their fall. When we want to understand the structure of atoms, we scatter particles off them and observe the results. In every case, we're using our instruments to probe nature and discover what's actually there. But with the speed of light, we've reached a boundary where the normal process of scientific measurement breaks down in the most fascinating way imaginable. It's not that our instruments aren't sensitive enough or that the phenomena are too exotic to observe. It's that the very concepts of space and time that we use to make any measurement at all are themselves defined in terms of the speed of light. This creates what philosophers of science call a bootstrap paradox. We're pulling ourselves up by our own conceptual bootstraps, defining the fundamental framework of reality in terms of itself. And remarkably, this isn't a bug in our understanding of the universe, it's a feature. It reveals something profound about how deeply interconnected the basic structures of reality actually are. To understand how we arrived at this remarkable situation, we need to journey back through the history of attempts to pin down light speed. Each attempt taught us something crucial about the nature of light, space, and time, gradually building toward the revolutionary realization that would change everything. The first serious attempt to measure the speed of light came from an unlikely source, not a laboratory physicist, but an astronomer peering through telescopes at the moons of Jupiter. Ola Roma, working at the Paris Observatory in the 1670s, noticed something peculiar about the timing of eclipses in the Jovian system. As he watched Io, Jupiter's innermost large moon, disappear behind the planet and emerge again, he discovered that these eclipses didn't happen exactly when his calculations predicted they should. When Earth was moving toward Jupiter in its orbit, the eclipses appeared to happen slightly earlier than expected. When Earth was moving away from Jupiter, they appeared to happen slightly later. Roma realized he was witnessing something extraordinary. The light from these distant eclipses was taking time to travel across the solar system, and that travel time changed as the distance between Earth and Jupiter changed. By carefully timing these variations over months of observations, he calculated that light must travel at a finite speed, roughly 200,000 kilometers per second. This was revolutionary. For most of human history, light had been assumed to travel instantaneously. The idea that there could be a delay between an event happening and our seeing it challenged fundamental assumptions about the nature of observation and reality itself. Roma had opened a door to understanding that would eventually lead to relativity theory and our modern conception of space-time. But notice what Roma actually accomplished. He didn't measure the speed of light directly. He measured time intervals between astronomical events and compared them to distances in the solar system. His calculation depended on knowing how far Earth travels in its orbit, which depended on measurements of planetary distances, which themselves involved complex chains of assumptions about geometry, gravity, and the nature of celestial mechanics. This pattern would repeat throughout the history of light speed determination. Each experiment that claimed to measure light speed was actually measuring something else and inferring the speed through a web of other physical relationships and theoretical assumptions. The next major breakthrough came from Armand Fizeau in 1849, working in the suburbs of Paris with an ingenious mechanical apparatus. Fizeau used a rapidly spinning gear wheel with gaps between the teeth. He would shine light through one gap, reflect it off a distant mirror, and observe whether the returning light could pass back through another gap in the wheel. By adjusting the wheel's rotation speed, Fizeau could find the precise rate at which the returning light would be blocked by a tooth or allowed through a gap. From the wheel's rotation speed, the spacing of the teeth, and the distance to the mirror, he calculated light speed at about 313,000 kilometers per second, remarkably close to the modern value. But again, let's examine what Fizeau actually measured. He measured the rotation rate of his wheel, which depended on mechanical timing mechanisms. He measured the distance to his mirror using surveying techniques and standard length measurements. He was comparing electromagnetic phenomena, light, with mechanical phenomena, spinning wheels, and measured distances. What made his result meaningful wasn't that he had somehow directly observed light in motion. It was that his measurement fit consistently with other physical relationships and theoretical expectations. His experiment worked because it embedded light speed determination within a broader framework of mechanical and optical measurements that all had to be mutually consistent. Léon Foucault refined this approach in the 1850s, using rotating mirrors instead of gear wheels and achieving even greater precision. Albert Michelson spent decades perfecting interferometric techniques that could detect incredibly tiny differences in light travel time. Each generation of experimenters achieved better and better precision, seemingly getting closer and closer to the true speed of light. But as these measurements became more precise, physicists began to notice something troubling. Different experimental methods sometimes gave slightly different results. More importantly, the concept of what it meant for light to have a speed was becoming increasingly problematic as theoretical understanding advanced. The trouble started with James Clerk Maxwell's electromagnetic theory in the 1860s. Maxwell showed that light was an electromagnetic wave, a propagating disturbance in electric and magnetic fields. His equations predicted that electromagnetic waves should travel at a specific speed in vacuum, a speed determined by fundamental properties of space itself. This raised a disturbing question. If light is a wave, what is it waving in? All other waves that physicists knew about required a medium. Sound waves travel through air or water. Waves on a string travel along the string itself. What medium could support light waves traveling through the apparent emptiness of space? The answer seemed obvious. There must be an invisible substance filling all of space, something subtle enough to allow planets to orbit freely, but substantial enough to support electromagnetic waves. They called this hypothetical substance the luminiferous ether. If the ether existed, then the speed of light should depend on motion relative to this cosmic medium. Just as sound travels at different speeds relative to a moving observer depending on wind conditions, light should travel at different speeds, depending on how fast you're moving through the ether. This led to one of the most famous experiments in the history of physics, the Michelson-Morley experiment of 1887. Using an incredibly sensitive interferometer, Albert Michelson and Edward Morley attempted to detect Earth's motion through the ether by comparing the speed of light in different directions. They expected to find that light travels slightly faster or slower, depending on whether it's moving with or against Earth's motion through the ether. Instead, they found nothing. No matter which direction they pointed their apparatus, no matter what time of day or what season they performed the experiment, the speed of light remained exactly the same. this null result was more than just a failed experiment. It was a crisis that shook the foundations of physics. Either dragged along with the ether was being Earth in some impossible way, or the experimental apparatus was somehow contracting in the direction of motion, or something much more fundamental was wrong with physicists' understanding of space, time, and motion. The resolution came from a young patent clerk named Albert Einstein, who made a radical proposal. What if the Michelson-Morley experiment wasn't a failure? What if it was telling us something profound about the nature of reality itself? Einstein suggested that the speed of light isn't relative to some invisible ether, but is instead the same for all observers, regardless of how fast they're moving. This seemingly simple statement had staggering implications that would revolutionize our understanding of space and time. If the speed of light is the same for everyone, then space and time themselves must be flexible, stretching and compressing to ensure that light always travels at the same speed, no matter who's measuring it. This was the birth of special relativity, and it changed everything. But even Einstein's breakthrough didn't solve the measurement problem. If anything, it made the situation more puzzling. Special relativity showed that space and time are intimately connected, that the speed of light is the conversion factor between spatial and temporal measurements. But this made the question of measuring light speed even more circular than before. In Einstein's framework, asking for the speed of light is like asking how many centimeters are in a meter. The answer isn't discovered through measurement, it's established by the definition of the units themselves. The speed of light becomes the fundamental constant that determines the relationship between space and time measurements. This realization gradually dawned on the physics community throughout the 20th century. As quantum mechanics developed and our understanding of fundamental constants deepened, it became clear that the speed of light occupied a unique position in the architecture of physical law. Unlike other constants like the mass of the electron or the strength of the electromagnetic force, which seem to be arbitrary numbers that nature happens to have chosen, the speed of light appeared to be something more fundamental. It wasn't just a property of light, it was a property of space-time itself. The final nail in the coffin of light speed measurement came in 1983, when the international scientific community made a remarkable decision. Instead of continuing to refine measurements of the speed of light, they would define it to have an exact value and use that definition to establish the fundamental units of length and time. This wasn't giving up on measurement, it was recognizing the deep logical structure that underlies all measurement. The speed of light had become so central to our understanding of physics that it made more sense to use it as a foundation for defining other quantities, rather than trying to measure it in terms of those quantities. Today, the meter is defined as the distance light travels in exactly 1 divided by 299,792,458 of a second in vacuum. This isn't an approximation or a measurement result. It's a definition that makes the speed of light exactly 299,792,458 meters per second by construction. But this raises profound questions about the nature of physical knowledge. If we've defined the speed of light rather than measured it, what does this say about our understanding of the universe? Are we discovering objective truths about nature, or are we constructing frameworks for organizing our observations? The answer reveals something beautiful about how science actually works. The speed of light occupies a special place in physics, not because we've measured it precisely, but because it represents a deep symmetry in the structure of space-time itself. It's the speed at which causality propagates, the maximum rate at which information can travel, the fundamental tempo at which reality unfolds. This fundamental tempo isn't something we discovered hiding in nature, like a buried treasure waiting to be unearthed. Instead, it's something we recognized as being so central to the architecture of reality that it serves as the cornerstone upon which we build our entire framework for understanding space and time. Think about it this way. When you're building a house, you don't measure the foundation after the house is complete. The foundation comes first, and everything else is built relative to it. The speed of light has become the foundation of modern physics, the reference point that gives meaning to all our other measurements. But this creates a fascinating puzzle that goes to the heart of how scientific knowledge actually works. We often think of science as a process of discovery, of uncovering hidden truths about the natural world through careful observation and experimentation. Yet here we have one of the most important constants in all of physics, and we've essentially decided what its value should be rather than measuring it. This might seem like cheating, like we've somehow abandoned the scientific method in favor of arbitrary human decisions. But the reality is far more subtle and beautiful than that. What we've actually done is recognized that certain relationships in nature are so fundamental that they transcend the normal distinction between discovery and definition. Let me share an analogy that might help illuminate this. Imagine you're a cartographer trying to map an unknown continent. You start by picking a reference point, maybe a distinctive mountain peak, and you declare that this point has coordinates 0, 0 on your map. This isn't a measurement, it's a choice. But once you've made that choice, the positions of all other features on your map can be determined through careful measurement relative to your chosen reference point. The speed of light plays a similar role in the map of physical reality. It's not that we've measured it to be 299,792,458 meters per second. It's that we've chosen this as our fundamental reference point for understanding the relationship between space and time, and all our other measurements of distances and durations are made relative to this standard. But here's where the analogy breaks down in a fascinating way. Unlike a cartographer's arbitrary choice of coordinates, the speed of light isn't arbitrary at all. It emerges from the deep mathematical structure of space-time itself, from the geometry that underlies all physical phenomena. Einstein's equations don't just happen to contain this particular speed. They reveal that space-time has an inherent structure, a fundamental geometry that determines how matter and energy can move and interact. The speed of light is written into this geometry as surely as the ratio of a circle's circumference to its diameter is written into the structure of flat space. This is why attempts to measure the speed of light always led to the same result, regardless of the experimental method used. It wasn't because experimenters were getting better and better at measuring some arbitrary property of light. It was because they were gradually discovering a fundamental feature of the universe itself, something so basic that it shapes every physical process and every possible measurement. The impossibility of measuring the speed of light reveals something profound about the nature of physical constants. We tend to think of constants as numbers that nature has somehow chosen, like cosmic lottery balls that happen to come up with particular values. But some constants, like the speed of light, are different. They're not chosen by nature so much as they define what nature is. Consider the mathematical constant pi. We don't measure pi by carefully drawing circles and dividing circumference by diameter, hoping to get more and more accurate values. We know pi exactly through mathematical reasoning, and we use that exact value to make predictions about circular geometry. Pi isn't discovered through measurement, it's revealed through understanding the logical structure of mathematics itself. The speed of light has become the pi of space-time. It's not a measured quantity, but a fundamental aspect of the geometric structure that underlies all physical phenomena. Just as pi tells us about the relationship between different measurements in circular geometry, the speed of light tells us about the relationship between space and time measurements in the geometry of space-time. This realization transforms how we think about the role of measurement in physics. Measurement isn't just about determining the values of pre-existing quantities. It's about discovering the relationships between different aspects that connect of reality, the patterns seemingly separate phenomena into a unified whole. When Romer observed the eclipses of Jupiter's moons, he wasn't really measuring the speed of light. He was discovering that astronomical observations made at different times and places could be connected through a simple mathematical relationship. When Fizeau spun his gear wheel, he wasn't measuring light speed directly. He was finding that mechanical rotations and optical phenomena follow predictable patterns that reveal deeper connections in nature. Each of these experiments contributed to our growing understanding of how different physical phenomena relate to each other. They weren't failed attempts at measurement so much as successful explorations of the hidden connections that bind the universe together. This perspective helps us understand why the speed of light appears in so many different areas of physics. It's not because light is somehow special or fundamental in itself. It's because the speed of light represents a deep structural feature of space-time that influences every physical process. When you see the speed of light appearing in Einstein's mass-energy equation, it's not there because the equation is about light. It's there because the equation is about the conversion between different forms of energy, and that conversion rate is determined by the fundamental structure of space-time itself. When the speed of light appears in the equations of electromagnetism, it's not because those equations describe light specifically. It's because electromagnetic phenomena propagate through space-time, and the speed of that propagation is determined by space-time's geometric properties. Even in quantum mechanics, where particles can behave in ways that seem to violate our everyday understanding of space and time, the speed of light still appears as a fundamental limit. Quantum effects can't propagate faster than light. Quantum information can't be transmitted faster than light. And even the strangest quantum phenomena respect this cosmic speed limit. This universality isn't coincidental. It reflects the fact that the speed of light isn't really about light at all. It's about the fundamental structure of the stage on which all physical phenomena play out. Every process, every interaction, every change in the universe happens within the framework of space-time, and that framework has built-in properties that determine how quickly information and influence can propagate. But this raises an even deeper question. If the speed of light is so fundamental to the structure of reality, where does that structure come from? Why does space-time have the particular geometry it does? Why is the cosmic speed limit what it is, rather than something else? These questions push us toward the very edges of human understanding. They touch on fundamental issues about the nature of existence itself. Is the geometry of space-time something that could have been different? Or is it somehow logically necessary? Are there other possible universes with different space-time structures, different cosmic speed limits, different relationships between space and time? Modern physics has begun to explore these mind-bending possibilities through theories like string theory and quantum gravity. These approaches suggest that space-time itself might not be fundamental, but might emerge from something even more basic. Just as temperature emerges from the random motions of molecules, space-time might emerge from some deeper level of reality that we're only beginning to glimpse. If this is true, then the speed of light might not be the most fundamental constant after all. It might be a secondary feature that emerges from whatever gives rise to space-time itself. But even if that's the case, it doesn't diminish the profound role that light speed plays in organizing our current understanding of physics. The impossibility of measuring the speed of light has taught us something crucial about the nature of scientific knowledge. It's shown us that the most fundamental truths about reality might not be things we can measure directly, but relationships we can recognize through the patterns that connect all our observations. This has implications that extend far beyond physics. It suggests that the deepest understanding often comes not from accumulating more and more precise measurements, but from recognizing the underlying structures that make measurement possible in the first place. In mathematics, we don't understand numbers by measuring them with increasingly precise rulers. We understand them through their relationships to each other, through the patterns that emerge when we explore how they behave under different operations. Similarly, we understand the physical world not just by measuring its properties, but by discovering the relationships that connect different phenomena. The speed of light stands as a monument to this deeper kind of understanding. It reminds us that the universe isn't just a collection of separate objects with measurable properties. It's an interconnected whole where the most fundamental features are relationships rather than things. This interconnectedness extends to the very process of measurement itself. Every time we measure anything, we're comparing it to something else, relating it to some standard or reference point. The choice of reference points isn't arbitrary. It reflects the deep structure of whatever we're trying to understand. When we chose to define the speed of light as exactly 299,792,458 meters per second, we weren't making an arbitrary decision. We were recognizing that this particular relationship has become so central to our understanding of space and time that it makes sense to use it as the foundation for defining spatial and temporal measurements. This decision reflects centuries of experimental work and theoretical development that gradually revealed the fundamental role that light speed plays in the architecture of physics. It's the culmination of a long journey of discovery that began with Romer's observations of Jupiter's moons and led through Maxwell's electromagnetic theory, Einstein's relativity, and quantum field theory to our modern understanding of space-time structure. But the journey isn't over. As we push toward even more fundamental theories of quantum gravity and the nature of space-time itself, we may discover that the speed of light is just one manifestation of even deeper principles that govern the structure of reality. The impossibility of measuring the speed of light has opened doors rather than closing them. It's led us to understand that measurement and definition are more intertwined than we once thought, that the deepest truths about nature might be structural rather than numerical, and that the universe reveals itself not just through what we can measure, but through the relationships that make measurement meaningful. As you contemplate these ideas, remember that you're participating in one of humanity's greatest intellectual adventures. The recognition that we cannot measure the speed of light isn't a limitation of human knowledge. It's a window into the profound interconnectedness that underlies all of reality. This realization brings us to one of the most beautiful paradoxes in all of science. The very thing that makes it impossible to measure the speed of light is also what makes the universe comprehensible in the first place. Without this fundamental constant serving as the backbone of space-time, there would be no stable framework within which any measurement could have meaning. Think about what this means for a moment. Every ruler you've ever used, every clock you've ever watched, every GPS satellite guiding you home depends on this unmeasurable constant. The meter stick in your drawer exists because we've agreed that light travels a certain distance in a certain time. The atomic clocks that keep our digital world synchronized tick at rates determined by electromagnetic processes that unfold at light speed. You're living inside a measurement system that bootstraps itself into existence through this itself be measured. It's like discovering cosmic constant that the foundation of your house is somehow holding itself up, creating its own support through some impossible architectural feat that defies everything you thought you knew about construction. But here's where the story takes an even more fascinating turn. While we cannot measure the speed of light, we can measure how it relates to other fundamental constants of nature. And these relationships reveal something extraordinary about the deep structure of reality itself. Consider the fine structure constant, a dimensionless number that characterizes the strength of electromagnetic interactions. This constant emerges from a specific combination of the speed of light, the elementary charge, and Planck's constant. Unlike the speed of light, the fine structure constant can be measured experimentally, and it comes out to approximately 1 divided by 137. This number has puzzled physicists for nearly a century. Why, or 200,137? Why not 100 or any other value? The fine structure constant seems to be one of those genuine mysteries where nature has chosen a specific value for reasons we don't yet understand. Unlike the speed of light, which emerges from the geometry of space-time itself, this constant appears to be a true measured quantity that characterizes how strongly electromagnetic forces operate in our universe. The relationship between these two very different kinds of constants reveals something profound about how physics actually works. Some aspects of nature, like the speed of light, are structural features that define the framework within which physics operates. Others, like the fine structure constant, appear to be genuine parameters that characterize how specific forces and particles behave within that framework. This distinction helps us understand why attempts to measure the speed of light were doomed from the start, while measurements of other constants can yield genuine discoveries about the nature of reality. When you measure the mass of an electron, you're probing a real feature of how matter behaves. When you measure the strength of gravitational attraction, you're discovering something about how space and time respond to the presence of mass and energy. But when you try to measure the speed of light, you're essentially trying to measure the exchange rate between space and time themselves. It's like trying to determine how many inches are in a foot by using a ruler that's calibrated in terms of feet and inches. The question contains its own answer, built into the definitions of the terms you're using. This realization has profound implications for how we think about the nature of physical law. Laws of physics aren't just descriptions of how things behave. They're statements about the relationships that must hold between different aspects of reality for the universe to be logically consistent. The fact that nothing can travel faster than light isn't just an empirical observation about the behavior of particles and waves. It's a logical requirement that emerges from the structure of space-time itself. If information could propagate faster than light, it would create causal paradoxes that would make the universe logically inconsistent. The speed of light serves as a cosmic firewall that prevents such paradoxes from arising. Similarly, the relationship between mass and energy encoded in Einstein's famous equation isn't just a curious fact about how matter behaves. It's a statement about the fundamental equivalence between different forms of physical reality. Mass and energy aren't separate things that happen to be related by some conversion factor. They're different aspects of the same underlying reality, and the speed of light squared is the conversion factor that reveals their deep unity. These insights transform how we understand the role of measurement in physics. Measurement isn't just about determining numerical values. It's about discovering the logical relationships that must hold between different aspects of reality for the universe to make sense. When physicists measure the properties of subatomic particles in accelerator experiments, they're not just cataloging the features of tiny objects. They're exploring the logical constraints that determine what kinds of particles can exist and how they can interact. When astronomers measure the expansion rate of the universe, they're not just determining how fast galaxies are moving away from us. They're probing the logical structure that governs how space-time itself can evolve over cosmic time. The impossibility of measuring as a perfect The speed of light stands example of how the deepest insights in physics often come from recognizing what cannot be measured rather than what can. Sometimes the most profound truths are revealed not by pushing our instruments to greater precision, but by understanding the logical limits that constrain all possible measurements. This perspective helps explain why theoretical physics has become increasingly important in our quest to understand the fundamental nature of reality. As we probe deeper into the foundations of physics, we encounter more and more situations where the traditional approach of measurement and experimentation reaches its limits, not because of technological constraints, but because of logical ones. String theory, quantum gravity, and theories of multiple universes all deal with phenomena that may be fundamentally unmeasurable, not because they're too small or too distant, but because they exist beyond the boundaries of what measurement can meaningfully address. These theories don't abandon empirical science so much as they extend it into realms where logical consistency becomes as important as experimental verification. The speed of light serves as our guide into these strange territories. Its unmeasurability isn't a limitation of human knowledge. It's a signpost pointing toward deeper truths about the logical structure that underlies all physical phenomena. But this raises a question that goes to the very heart of what it means to understand the universe. If some of the most fundamental features of reality cannot be measured, how can we ever hope to truly understand them? How do we distinguish between genuine insights about the nature of existence and mere mathematical constructions that have no connection to physical reality? The answer lies in recognizing that understanding doesn't always require measurement. Sometimes the deepest insights come from recognizing patterns, symmetries, and logical relationships that transcend any particular set of numerical values. Consider the role that symmetry plays in modern physics. When physicists discovered that the laws of physics weren't making measurements in the traditional sense. They were recognizing patterns the same under certain transformations, they in the logical structure of physical law. These symmetry principles have led to some of the most profound discoveries in physics, from the conservation laws that govern energy and momentum to the unified theories that connect different fundamental forces. The speed of light emerges from one such symmetry, the Lorentz symmetry that underlies special relativity. This symmetry expresses the idea that the laws of physics should look the same to all observers moving at constant velocities relative to each other. The speed of light isn't an arbitrary constant that nature happens to have chosen. It's the natural consequence of this symmetry principle applied to the structure of space-time. Understanding this symmetry gives us insight into why the speed of light has the fundamental role it plays in physics. It's not because light itself is somehow special or fundamental. It's because this particular speed emerges naturally from the requirement that physical law should be logically consistent for all observers. This kind of understanding transcends measurement in the traditional sense. We don't need to measure the speed of light to understand why it plays such a crucial role in physics. We need to understand the logical principles that give rise to it, and the relationships that connect it to other aspects of physical reality. The same pattern appears throughout modern physics. Quantum mechanics doesn't just give us rules for calculating the probabilities of different measurement outcomes. It reveals deep logical constraints on what kinds of measurements are possible and how different measurements relate to each other. The uncertainty principle isn't just a statement about the limitations of our measuring instruments. It's a logical requirement that emerges from the mathematical structure of quantum theory itself. General relativity doesn't just tell us how massive objects curve space-time. It reveals the logical relationship between geometry and gravity, showing us that what we experience as gravitational force is actually the curvature of the space-time through which we move. The equations of general relativity aren't just formulas for calculating planetary orbits. They're expressions of the logical consistency requirements that any theory of gravity must satisfy. These examples illustrate how the impossibility of measuring the speed of light fits into a broader pattern in physics. The most fundamental insights often come from recognizing logicalist truths about reality, our relationships, rather than measuring numerical values. The deep structural rather than quantitative. This doesn't mean that measurement becomes unimportant. Experimental verification remains crucial for testing our theoretical understanding and discovering new phenomena. But it does mean that the role of measurement in physics is more subtle than we might initially suppose. Measurement doesn't just tell us what the values of physical constants are. It helps us discover the logical relationships that connect different aspects of reality. When we recognize that the speed of light cannot be measured, we're not discovering a limitation of experimental physics. We're discovering something profound about the logical structure that underlies all physical phenomena. We're glimpsing the deep unity that connects space and time, matter and energy, cause and effect, into a single coherent framework for understanding the universe. This unity extends far beyond the speed of light itself. It reveals itself in the mathematical elegance of physical law, in the deep connections between seemingly separate phenomena, and in the remarkable fact that the universe appears to be comprehensible to rational inquiry at all. The impossibility of measuring the speed of light reminds us that the universe isn't just a collection of separate objects with measurable properties. It's an interconnected whole where the deepest truths are relationships rather than things, patterns rather than particles, principles rather than particular facts. As you contemplate these ideas, you're participating in one of the most remarkable features of human consciousness. You're able to recognize logical relationships that transcend any particular measurement or observation. You're glimpsing the abstract principles that govern the structure of physical reality itself. This capacity for recognizing patterns and relationships is what allows us to understand aspects of the universe that we cannot directly measure. It's what enables theoretical physics to make predictions about phenomena that exist beyond the reach of current experiments. It's what gives us confidence that our understanding of reality extends beyond the particular corner of space and time that we happen to inhabit. The speed of light stands as a monument to this deeper kind of understanding. Its unmeasurability doesn't represent a failure of human knowledge. It represents a triumph of human insight, a recognition that some truths are too fundamental to be measured because they define the very framework within which measurement becomes possible. But our exploration of this profound constant has revealed something even more extraordinary. The impossibility of measuring the speed of light isn't just a curious fact about physics. It's a window into the deepest questions about the nature of existence itself. What does it mean for something to be real if it cannot be measured? How do we distinguish between the aspects of reality that exist independently of human observation and the aspects that emerge from the frameworks we use to organize our understanding? These questions push us toward the very boundaries of what rational inquiry can address. The speed of light exists at this boundary. It's simultaneously the most precisely known constant in all of physics and something that has never been measured in the traditional sense. It's both a feature of objective reality and a human construction that we use to define our units of measurement. It's both discovered and defined, both found and created. This paradoxical nature reflects something deep about the relationship between human knowledge and physical reality. We don't simply discover pre-existing truths about the universe through measurement and observation. We participate in a complex dance between discovery and construction, finding patterns in nature and creating frameworks for understanding those patterns. The speed of light embodies this dance in its purest form. It emerges from the objective structure of space-time itself, but it also serves as the foundation for the human frameworks we use to measure space and time. It's neither purely objective nor purely constructed, but something more subtle that transcends these simple categories. Understanding this helps us appreciate why the impossibility of measuring the speed of light has such profound implications for physics and philosophy. It reveals that the relationship between human knowledge and physical reality is far more complex and interesting than we might initially suppose. As we continue to push the boundaries of fundamental physics, we're likely to encounter more situations where the traditional distinction between measurement and definition breaks down. Theories of quantum gravity suggest that space and time themselves might not be fundamental features of reality, but emergent properties of something even more basic. If this is true, then all our measurements of spatial and temporal quantities might be based on frameworks that are themselves emergent rather than fundamental. String theory proposes that the fundamental constituents of reality are vibrating strings in higher dimensional spaces that we cannot directly observe. The properties of particles and forces that we can measure emerge from the vibrational patterns of these strings in ways that transcend traditional notions of measurement and observation. Theories of the multiverse suggest that our entire observable universe might be just one bubble in an infinite foam of possible realities, each with its own values for the fundamental constants of physics. If this is true, then the question of why physical constants have the values they do might not have answers in terms of measurement or logical necessity, but might instead reflect the anthropic selection effect that we exist in a universe compatible with our existence. These possibilities push us toward recognizing that the impossibility of measuring the speed of light might be just the beginning of a much deeper exploration of the boundaries of human knowledge. As we probe more deeply into the fundamental nature of reality, we may find that more and more of what we thought were measurable quantities are actually definitional frameworks that organize our understanding rather than objective features waiting to be discovered. This doesn't represent a retreat from empirical science, so much as an evolution toward recognizing the subtle interplay between discovery and construction that characterizes all human knowledge. The speed of light has taught us that some of the most important truths about reality transcend the simple distinction between what we measure and what we define. As we drift deeper into these contemplations, let yourself appreciate the remarkable journey we've taken together. We began with what seemed like a simple question about measuring the speed of light, and we've discovered profound truths about the nature of space-time, the role of symmetry in physics, the relationship between measurement and definition, and the boundaries of human knowledge itself. The impossibility of measuring the speed of light isn't a limitation we need to overcome. It's a doorway into deeper understanding of how the universe is structured and how human knowledge relates to physical reality. It reminds us that the most fundamental truths are often the ones that organize our thinking rather than the ones we can capture through measurement. Every time you flip a light switch, every time you check the time on your phone, every time you use GPS to navigate, you're relying on this unmeasurable constant that serves as the foundation for our understanding of space and time. The speed of light isn't just an abstract concept from theoretical physics. It's woven into the fabric of modern technology and modern life in ways that reveal its fundamental importance. Yet its true significance lies not in its practical applications, but in what it teaches us about the deep structure of reality itself. The speed of light is the cosmic constant that cannot be measured, the foundation that supports itself, the answer that defines the question rather than emerging from it. In recognizing why no one has measured the speed of light, we glimpse something beautiful about the logical elegance that underlies all physical phenomena. We discover that the universe isn't just a collection of measurable quantities, but a coherent logical structure where the deepest truths are relationships rather than things. As you settle into sleep tonight, carried by these thoughts about the unmeasurable constant that governs the flow of time itself, remember that you're part of this cosmic structure. Every thought in your mind propagates through neural networks at speeds ultimately limited by the speed of light. Every heartbeat, every breath, every moment of consciousness unfolds within the space-time framework that this constant defines. The speed of light may be unmeasurable, but it's also undeniably real. It shapes every aspect of physical reality, from the smallest quantum scales to the largest cosmic structures. And in recognizing why it cannot be measured, we touch something profound about the nature of existence itself. This realization transforms our entire understanding of what physical constants actually represent. Some constants, like the speed of light, aren't arbitrary numbers that nature happened to choose from some cosmic lottery. They're structural features that emerge from the logical requirements of a consistent universe. They're more like the rules of mathematics than like the properties of physical objects. But this raises a fascinating question that cuts to the heart of how we understand reality itself. If the speed of light is a structural constant rather than a measured quantity, what does that tell us about the other fundamental constants of nature? Are they all structural, or are some of them genuine discoveries about how the universe happens to be constructed? Consider the gravitational constant, the number that determines how strongly massive objects attract each other. Unlike the speed of light, this constant can be measured experimentally. We can drop objects, time their fall, and calculate how strong Earth's gravitational field must be. We can observe the orbits of planets and moons and determine how gravitational attraction varies with distance and mass. These measurements reveal that gravity follows very specific mathematical relationships, but the overall strength of gravitational attraction appears to be a genuine parameter that characterizes our particular universe. If gravity were twice as strong or half as weak, the mathematical relationships would remain the same, but stars would burn differently, planets would orbit at different distances, and the entire cosmic architecture would be transformed. This suggests a fascinating hierarchy in the constants of nature. Some, like the speed of light, are structural constants that emerge from the logical requirements of space-time geometry. Others, like the gravitational constant, appear to be environmental parameters that characterize the specific universe we happen to inhabit. The distinction becomes even more intriguing when we consider constants like the fine structure constant, that mysterious number approximately equal to 1 divided by 137 that characterizes the strength of electromagnetic interactions. This constant can be measured experimentally, and it seems to be a genuine feature of our universe rather than a structural necessity. But here's where things get really strange. The fine structure constant appears to be dimensionless, meaning it doesn't depend on our choice of units for measuring length, time, or mass. It's a pure number that characterizes the relative strength of electromagnetic and gravitational forces. Unlike the speed of light, which has units of velocity and depends on how we define meters and seconds, the fine structure constant seems to represent something more fundamental about the intrinsic structure of reality. This dimensionless nature makes the fine structure constant particularly puzzling. Why should it have the value it does rather than some other value? Unlike the speed of light, which emerges from space-time geometry, the fine structure constant appears to be a genuine mystery, where nature has chosen a specific value for reasons we don't understand. The interplay between these different types of constants reveals something profound about the architecture of physical law. The universe appears to be built on multiple levels, with structural constants like the speed of light defining the framework within which physics operates, and environmental constants like the fine structure constant and gravitational constant determining the specific character of physical phenomena within that framework. This multi-layered structure helps explain why some aspects of physics seem inevitable while others seem contingent. The speed of light plays the role it does because any universe with a consistent space-time structure must have some maximum speed for information propagation. But the specific values of the environmental constants seem to be genuine features of our particular cosmic neighborhood. The recognition of this hierarchy has profound implications for how we think about the relationship between physics and philosophy. Some features of reality, like the impossibility of faster-than-light travel, appear to be logical necessities that would hold in any possible universe. Others, like the specific strength of electromagnetic forces, seem to be empirical facts about the universe we actually inhabit. This distinction becomes especially important when we consider modern theories that suggest our universe might be just one of many possible universes, each with its own values for the environmental constants. In such a multiverse, the structural constants, like the speed of light, would remain the same across all universes, defining the basic framework of physics, while the environmental constants would vary from universe to universe. The anthropic principle suggests that we observe the particular values of environmental constants, that we do not because they're somehow preferred by nature, but because they're the values that allow complex structures like stars, planets, and life to exist. In universes where these constants had very different values, there might be no observers to wonder about the values of physical constants. This anthropic reasoning provides a potential explanation for why constants like the fine structure constant have the seemingly arbitrary values they do. They're not arbitrary at all, but are selected by the requirement that the universe be capable of supporting the kinds of complex processes that can give rise to conscious observers. But the anthropic principle raises as many questions as it answers. If there are indeed multiple universes with different values for the environmental constants, what determines the range of possible values? Are all conceivable combinations equally likely, or are there deeper principles that constrain the possibilities? These questions push us toward recognizing that the impossibility of measuring the speed of light is part of a much larger puzzle about the nature of physical reality. We live in a universe where some features seem to be logical necessities, while others appear to be contingent facts. Understanding the relationship between these different levels of reality is one of the deepest challenges facing modern physics and philosophy. The speed of light serves as our guide into these deep waters. Its unmeasurability isn't an isolated curiosity, but a window into the fundamental distinction between structural and environmental aspects of physical law. It reminds us that the universe has multiple layers of organization, from the geometric structure of space-time itself to the specific values of constants that determine how forces and particles behave within that structure. As we explore these layers more deeply, we begin to appreciate why the question of measuring the speed of light was ultimately the wrong question to ask. We weren't trying to determine an arbitrary parameter of nature. We were trying to uncover a structural feature of reality itself, something so fundamental that it defines the very framework within which measurement becomes possible. This realization has transformed how physicists approach the study of fundamental constants. Instead of simply trying to measure them more precisely, we now ask deeper questions about their relationships to each other and their roles in the overall architecture of physical law. The search for a theory of everything, a unified framework that would explain all the fundamental forces and particles, is really a search for understanding how the structural and environmental constants of nature relate to each other. Such a theory would reveal why the environmental constants have the values they do, and how those values emerge from deeper structural principles. String theory represents one ambitious attempt to achieve this unification. It suggests that all the fundamental constants of nature arise from the geometry of higher dimensional spaces that we cannot directly observe. In this framework, the environmental constants that seem arbitrary from our three-dimensional perspective would be revealed as inevitable consequences of the geometry of these hidden dimensions. Loop quantum gravity offers a different approach, suggesting that space-time itself might be discrete rather than continuous at the smallest scales. This discreteness could provide natural explanations for some of the mysterious constants of nature, relating them to the fundamental granularity of space and time. These theories remain highly speculative, but they illustrate how the impossibility of measuring the speed of light has opened up new ways of thinking about the deepest questions in physics. By recognizing that some constants are structural rather than environmental, we've learned to ask different kinds of questions about the foundations of physical reality. The speed of light has taught us that understanding doesn't always require measurement in the traditional sense. Sometimes the deepest insights come from recognizing logical relationships and structural principles that transcend any particular set of numerical values. This has profound implications for how we approach the study of phenomena that exist beyond the reach of direct observation. Consider the problem of understanding consciousness, one of the most mysterious phenomena we encounter. Traditional scientific approaches to consciousness often focus on measuring neural activity, mapping brain structures, and correlating mental states with physical processes. These approaches have yielded important insights, but they may be missing something fundamental about the nature of conscious experience itself. The lesson of the speed of light suggests that some aspects of consciousness might be structural rather than environmental, features that emerge from the logical organization of information processing rather than from the specific physical mechanisms that implement that processing. Understanding consciousness might require recognizing patterns and relationships that transcend the particular material substrate in which they're instantiated. Similarly, the study of complex systems, from ecosystems to economies to social networks, might benefit from focusing on structural principles rather than just measuring the properties of individual components. The speed of light has shown us that some of the most important truths about reality are organizational rather than quantitative. This perspective has implications that extend far beyond physics and into other areas of human inquiry. In mathematics, the most profound insights often come from recognizing abstract patterns and relationships rather than from calculating specific numerical values. In art and literature, the most powerful works often reveal universal human experiences through particular stories and images. The impossibility of measuring the speed of light reminds us that understanding is ultimately about recognizing patterns, relationships, and structures that connect different aspects of experience into coherent wholes. The deepest truths are often those that organize our thinking rather than those we can capture through direct observation. As you contemplate these ideas, you're engaging with questions that have puzzled humans for millennia. What is the relationship between the patterns we recognize in nature and the underlying reality that gives rise to those patterns? How do we distinguish between the aspects of our understanding that reflect genuine features of the world and the aspects that reflect the limitations or biases of our particular perspective? The speed of light offers no easy answers to these questions, but it does provide a remarkable example of how apparent limitations can become doorways to deeper understanding. The impossibility of measuring this fundamental constant has revealed profound truths about the structure of space-time. the nature of physical law, and the relationship between human knowledge and physical reality. Every photon of light that reaches your eyes has traveled at exactly this unmeasurable speed, carrying information encoded in electromagnetic waves that propagate according to principles we understand but cannot directly measure. The light from your reading lamp, the glow of stars visible through your window, the radiation from distant galaxies billions of light years away, all participate in this cosmic dance, governed by a constant that defines itself. In recognizing why no one has measured the speed of light, we've discovered something beautiful about the logical elegance underlying all physical phenomena. We've learned that the universe isn't just a collection of measurable quantities waiting to be catalogued, but a coherent structure where the deepest truths are relationships rather than things. The speed of light stands as a testament to the power of human reason to recognize patterns and principles that transcend direct observation. It reminds us that some of the most important features of reality are structural rather than quantitative, definitional rather than empirical, logical rather than merely factual. As we continue pushing toward ever more fundamental theories of reality, we're likely to encounter more situations where traditional notions of measurement and observation reach their limits. The speed of light has prepared us for these encounters by showing us that such limits aren't obstacles to understanding, but invitations to think more deeply about the nature of knowledge itself. The unmeasurable constant that governs the propagation of light through space and time has become our guide into territories where logic and mathematics become as important as experimentation and observation. It has shown us that the universe reveals its deepest secrets, not just through what we can measure, but through the patterns and principles that make measurement meaningful in the first place. Tonight, as photons from countless sources converge on your retina at exactly the speed that cannot be measured, you're witnessing one of the most fundamental processes in the universe. Light carries information, energy, and the very possibility of observation itself across vast distances at a speed that emerges from the logical structure of space-time. The impossibility of measuring this speed isn't a failure of human knowledge, but a triumph of human insight. It represents our recognition that some truths are too fundamental to be discovered through measurement because they define the very framework within which discovery becomes possible. As you drift towards sleep, carried by these thoughts about the unmeasurable foundation of measurable reality, remember that you're part of this cosmic structure. Your thoughts propagate through neural networks at speeds ultimately governed by electromagnetic processes that unfold at light speed. Your existence depends on countless physical processes that respect this unmeasurable constant. The speed of light may resist all attempts at direct measurement, but it permeates every aspect of physical reality, from the quantum scale to the cosmic horizon. In understanding why it cannot be measured, we touch something profound about the logical elegance that underlies all existence. The structural beauty that makes the universe comprehensible to rational minds, the constant that defines the relationship between space and time, remains forever beyond the reach of our measuring instruments, yet it shapes every measurement we make and every observation we perform. It stands as a monument to the subtle interplay between discovery and definition, between what we find in nature and what we construct to understand what we find. This profound realization about the unmeasurable nature of light speed opens up an even more fascinating territory when we consider what this means for the very foundations of scientific inquiry itself. You see, when we recognize that the speed of light cannot be measured, we're not just discovering something about electromagnetic radiation or space-time geometry. We're uncovering something fundamental about the nature of knowledge and the relationship between human understanding and physical reality. Let me guide you through this gentle revelation that has transformed how we think about the deepest questions in physics. The impossibility of measuring the speed of light reveals that science isn't just about accumulating more and more precise measurements of pre-existing quantities. It's about discovering the logical relationships that connect different aspects of reality into a coherent whole. This insight has rippled through every corner of modern physics, changing how we approach questions about the fundamental nature of existence. When physicists today work on theories of quantum gravity, they're not primarily trying to measure new quantities. They're trying to understand the logical relationships that must hold between quantum mechanics and general relativity for the universe to be mathematically consistent. When researchers explore the possibility of extra dimensions beyond the three spatial dimensions we directly experience, they're not attempting to measure these dimensions with rulers that extend into higher dimensional space. They're investigating the mathematical relationships that could explain why we observe the particular forces and particles that we do in our three-dimensional slice of reality. The speed of light has taught us that some of the most profound truths about the universe are structural rather than empirical. They emerge from the logical requirements of consistency rather than from direct observation of particular phenomena. This doesn't make them less real or less important. If anything, it makes them more fundamental because they represent constraints that any possible universe must satisfy to be logically coherent. Consider how this applies to one of the most mysterious aspects of our universe, the arrow of time. We experience time as flowing from past to future, with causes preceding their effects and entropy increasing as systems evolve from ordered to disordered states. Yet the fundamental equations of physics are largely time-symmetric, working equally well whether time flows forward or backward. The puzzle of time's arrow can't be solved by measuring time more precisely or building better clocks. Like the speed of light, the directionality of time appears to be a structural feature that emerges from the logical organization of physical processes rather than from some measurable property of time itself. The speed of light serves as our cosmic speed limit precisely because it ensures that cause and effect maintain their proper relationship. Information cannot propagate faster than light speed because doing so would allow effects to precede their causes, creating logical paradoxes that would undermine the coherent structure of space-time. This reveals something beautiful about how the universe protects its own logical consistency. The unmeasurable constant that governs light's propagation isn't just a feature of electromagnetic phenomena. It's a guardian of causality itself, ensuring that the story of the universe unfolds in a way that makes rational sense. But this protective role extends far beyond preventing temporal paradoxes. The speed of light also determines the fundamental structure of space itself through its relationship to the other constants of nature. When we combine the speed of light with Planck's constant and the gravitational constant, we get natural units for measuring length, time, and mass that don't depend on arbitrary human choices about the size of meters or the duration of seconds. These Planck units reveal the natural scales at which quantum effects and gravitational effects become equally important. The Planck length, roughly 10 to the minus 35 meters, represents the smallest distance that has any physical meaning within our current understanding of physics. Below this scale, the very concepts of space and distance break down as quantum fluctuations in the gravitational field become so violent that space-time itself loses its smooth, continuous character. The Planck time, the duration it takes light to travel one Planck length, represents the smallest interval of time that can be meaningfully defined. At shorter time scales, the quantum uncertainty in energy becomes so large that virtual particles and antiparticles pop in and out of existence with such frequency that the distinction between something and nothing becomes fundamentally blurred. These natural units emerge from combinations of fundamental constants, including the unmeasurable speed of light, suggesting that the structure of reality at its deepest level is determined by mathematical relationships rather than arbitrary physical parameters. The universe appears to be built on a foundation of logical consistency rather than random chance. This mathematical foundation helps explain why the speed of light appears in so many different areas of physics, from the equations that describe electromagnetic radiation, to the formulas that govern nuclear reactions, to the relationships that connect mass and energy. It's not because all these phenomena are somehow related to light specifically. It's because they all participate in the same underlying mathematical structure that governs how space, time, matter, and energy relate to each other. The impossibility of measuring the speed of light thus reveals something profound about the relationship between mathematics and physical reality. Mathematics isn't just a tool we use to describe natural phenomena. It appears to be the language in which the universe is written, the logical structure that determines what kinds of physical processes are possible and how they must relate to each other. This mathematical character of physical law has profound implications for how we understand the role of consciousness in the universe. The fact that human minds can recognize and understand the mathematical relationships that govern physical phenomena suggests a deep connection between the structure of rational thought and the structure of physical reality. When you contemplate the unmeasurable speed of light and understand why it cannot be measured, you're not just learning about a particular constant in physics. You're exercising the same kind of logical reasoning that gives rise to the mathematical structures underlying all physical phenomena. Your ability to grasp these abstract relationships reveals something remarkable about the nature of consciousness itself. This connection between mind and mathematics becomes even more intriguing when we consider that the speed of light governs the physical processes occurring in your brain right now. Every thought you think depends on electrochemical signals that propagate through your neural networks at speeds ultimately limited by the speed of light. The unmeasurable constant that shapes the structure of space-time also shapes the structure of the conscious experience through which you understand that structure. There's something almost mystical about this self-referential loop. The universe has evolved conscious beings capable of understanding the logical principles that govern the universe's own existence. The speed of light, which cannot be measured but defines the framework within which all measurement occurs, has somehow given rise to minds capable of recognizing why it cannot be measured. This suggests that consciousness might not be an accidental byproduct of complex physical processes, but rather a natural expression of the universe's inherent logical structure. Just as the speed of light emerges from the geometric properties of space-time, consciousness might emerge from the information processing properties that arise when matter and energy organize themselves into sufficiently complex patterns. The impossibility of measuring the speed of light thus becomes a window into some of the deepest questions about the nature of existence itself. It reveals that the universe is not just a collection of objects interacting according to mechanical laws, but a coherent logical structure where mind and matter, consciousness and cosmos participate in the same fundamental mathematical relationships. As you rest in these contemplations, allow yourself to appreciate the remarkable position you occupy in the cosmic story. You are a temporary arrangement of matter and energy that has become capable of understanding the logical principles that govern its own existence. The atoms that make up your body were forged in stellar cores through nuclear processes that respect the unmeasurable speed of light. The thoughts flowing through your mind propagate through neural networks governed by electromagnetic forces that operate at light speed. You are simultaneously part of the physical universe and capable of transcending it through rational understanding. You can grasp abstract mathematical relationships that exist independently of any particular physical instantiation. You can recognize logical principles that would remain true even if the universe had evolved very differently than it actually has. This capacity for abstract thought represents one of the most remarkable features of the universe we inhabit. Through billions of years of cosmic evolution, matter has organized itself into patterns complex enough to understand the mathematical structures underlying their own existence. The speed of light, which governs the propagation of information through space and time, has somehow enabled the emergence of information processing systems capable of understanding why it cannot be measured. The story of the unmeasurable speed of light is thus not just a story about physics or mathematics. It's a story about the evolution of understanding itself, about how the universe has become capable of knowing itself through the conscious beings it has produced. Every time you recognize a logical relationship or understand a mathematical principle, you're participating in this cosmic process of self-understanding. This perspective transforms how we think about the relationship between scientific knowledge and human meaning. Science isn't just about accumulating facts about the natural world. It's about participating in the universe's ongoing process of coming to understand itself. When we recognize why the speed of light cannot be measured, we're not just learning about a technical detail of physics, we're glimpsing the logical elegance that underlies all existence. The unmeasurable nature of this fundamental constant reminds us that the deepest truths about reality often transcend the simple distinction between subjective and objective, between discovered and constructed, between mind and matter. The speed of light exists at the intersection of all these categories, simultaneously defining the structure of physical space-time and serving as the foundation for human frameworks of measurement and understanding. As we continue pushing toward ever more fundamental theories of reality, this intersection becomes increasingly important. Theories of quantum consciousness suggest that the distinction between mind and matter might break down at the deepest levels of physical reality. Theories of information-based physics propose that information processing, rather than matter and energy, might be the most fundamental aspect of existence. The speed of light serves as our guide into these speculative territories. Its unmeasurable nature has prepared us to think about aspects of reality that transcend traditional notions of measurement and observation. It has shown us that some of the most important truths about existence are structural rather than empirical, logical rather than merely factual. This doesn't mean that empirical science becomes unimportant. Experimental verification remains crucial for testing our theoretical understanding and discovering new phenomena. But it does mean that the role of logic, mathematics, and abstract reasoning becomes increasingly central as we probe the deepest foundations of reality. The impossibility of measuring the speed of light has thus opened up new ways of thinking about what it means to understand the universe. Understanding doesn't always require measurement in the traditional sense. Sometimes it requires recognizing patterns, relationships, and logical principles that transcend any particular set of observational data. This expanded notion of understanding has profound implications for how we approach other deep mysteries of existence. Questions about the nature of consciousness, the origin of the universe, the possibility of other dimensions, and the ultimate fate of cosmic evolution all involve aspects that may be fundamentally unmeasurable in traditional terms. Yet these questions remain meaningful and potentially answerable through the same kind of logical reasoning that reveals why the speed of light cannot be measured. By recognizing structural principles and mathematical relationships, we may be able to understand aspects of reality that will forever remain beyond the reach of direct empirical investigation. The speed of light thus stands as more than just a fundamental constant of physics. It represents a new way of thinking about the relationship between human knowledge and physical reality. A recognition that some of the deepest truths about existence are logical rather than empirical, structural rather than quantitative. As you drift deeper into these contemplations, remember that you are witnessing something extraordinary in the history of human understanding. For the first time in our species' existence, we have recognized that one of the most fundamental features of physical reality cannot be measured, not because of technological limitations, but because of logical principles that transcend measurement itself. This recognition represents a new chapter in humanity's ongoing quest to understand the universe. It shows us that reality is even stranger and more wonderful than we had imagined, filled with unmeasurable constants that define the very framework within which measurement becomes possible. The gentle paradox of the unmeasurable speed of light continues to ripple through every corner of modern physics, revealing new layers of mystery even as it resolves old puzzles. Tonight, as you contemplate these profound truths about the nature of existence, you're participating in one of the most remarkable intellectual adventures in human history. The recognition that some of the deepest features of reality transcend the traditional boundaries between discovery and definition, between mind and matter, between the measurable and the unmeasurable. The speed of light remains forever beyond the reach of our instruments, yet it shapes every aspect of physical reality and every moment of conscious experience. In understanding why it cannot be measured, we touch something profound about the logical elegance that makes existence itself possible, the mathematical beauty that underlies all phenomena, and the mysterious connection between the structure of rational thought and the structure of physical reality. This understanding brings us to perhaps the most mind-bending realization of all. When we truly grasp why the speed of light cannot be measured, we discover that we're not just learning about a quirk of electromagnetic radiation or a technical limitation of scientific instruments. We're uncovering something fundamental about how reality constructs itself from moment to moment, how the universe maintains its own internal consistency through principles so elegant they almost seem too beautiful to be accidental. Let me guide you through this final layer of understanding, where physics touches something that feels almost mystical in its profundity. The speed of light doesn't just govern how fast information can travel through space. It governs how fast reality itself can update, how quickly the universe can transition from one moment to the next while maintaining logical coherence across all scales of existence. Think about what this means for your direct experience right now. Every sensation reaching your consciousness, every thought forming in your mind, every perception of the world around you depends on electromagnetic processes unfolding at precisely the speed that cannot be measured. The boundary between your inner subjective experience and the external objective world is mediated by this unmeasurable constant. When photons from distant stars enter your eyes after journeying for years across the cosmos, they carry not just energy and information, but time itself. They transport moments from the past directly into your present awareness, creating a bridge across space-time that connects your consciousness to events that occurred before you were born, in places you will never visit. This temporal bridging reveals something profound about the nature of existence itself. The unmeasurable speed of light doesn't just set limits on how fast things can move through space. It creates the very possibility of connection across space and time, the fundamental mechanism by which separate events can influence each other and thereby participate in a coherent cosmic story. But here's where the mystery deepens even further. Quantum mechanics has revealed that reality at its smallest scales doesn't behave like the familiar world of classical physics. Particles exist in superposition, occupying multiple states simultaneously until observed. They become entangled across vast distances, sharing correlations that seem to transcend the normal limitations of space-time separation. Yet even in this strange quantum realm, the unmeasurable speed of light maintains its role as the ultimate arbiter of causality. Quantum effects may appear instantaneous, but they cannot be used to send information faster than light speed. The universe protects its own logical consistency even in the face of quantum weirdness, ensuring that cause and effect maintain their proper temporal relationship. This protection extends to the very foundations of scientific measurement itself. Every instrument we use to probe quantum phenomena, every detector that registers the arrival of particles, every clock that times quantum processes, operates according to principles that ultimately respect the unmeasurable speed of light. We are embedded within the very system we're trying to understand, using tools that participate in the phenomena they're designed to measure. This creates a kind of cosmic recursion that goes far beyond the simple circularity we encountered when trying to measure light speed with rulers and clocks defined in terms of light speed. We discover that consciousness itself, the very capacity for awareness that makes measurement and understanding possible, emerges from physical processes governed by the same unmeasurable constant that defines the structure of space-time. Your ability to contemplate these ideas right now depends on neural networks processing information at speeds ultimately limited by electromagnetic propagation. The thoughts forming in your mind as you consider the unmeasurable nature of light speed are themselves constrained by that same unmeasurable limit. You are using a system governed by unmeasurable principles to understand why those principles cannot be measured. This recursive relationship between mind and cosmos suggests something extraordinary about the nature of understanding itself. Perhaps the reason human consciousness can grasp abstract mathematical relationships and logical principles is that consciousness emerges from the same mathematical structures that govern physical reality. The universe may be comprehensible to rational minds, precisely because rational minds are expressions of the universe's own logical structure. The impossibility of measuring the speed of light thus becomes a window into the deepest questions about existence, consciousness, and the relationship between mind and reality. It reveals that these aren't separate problems, but different aspects of a single mystery about how logical coherence manifests itself across all scales of existence, from quantum particles to cosmic structures to conscious experience. As we approach the culmination of our exploration, consider how this understanding transforms your relationship to the physical world around you. You are not separate from the universe, observing it from some privileged external position. You are the universe becoming aware of itself, a temporary pattern in the cosmic dance that has evolved the capacity to recognize the logical principles governing its own existence. Every breath you take involves molecular processes governed by quantum mechanics operating within the constraints imposed by the unmeasurable speed of light. Every heartbeat depends on electrical signals propagating through biological tissues at speeds that respect this fundamental limit. Every moment of consciousness represents the universe examining itself through patterns of neural activity that unfold according to the same principles that govern the propagation of light across cosmic distances. The unmeasurable constant that defines the relationship between space and time also defines the relationship between your inner experience and the external world. It sets the pace at which information flows between your senses and your awareness, determines how quickly your thoughts can form and transform, establishes the temporal rhythms within which your consciousness operates. This intimate connection between the unmeasurable speed of light and the nature of conscious experience reveals something beautiful about the role of mystery in human understanding. The fact that this fundamental constant cannot be measured doesn't represent a limitation of human knowledge. It represents an invitation to recognize that some truths transcend the traditional boundaries between subjective and objective, between mind and matter, between discovered and constructed. The speed of light exists at the intersection of all these categories, simultaneously defining the objective structure of physical space-time and serving as the foundation for subjective frameworks of understanding and measurement. It reminds us that reality is not just a collection of measurable quantities waiting to be catalogued, but a coherent logical structure where the deepest truths are relationships rather than things. As you drift towards sleep tonight, carried by these contemplations about the unmeasurable foundation of measurable reality, remember that you are participating in something magnificent. You are part of the universe's ongoing process of understanding itself, a conscious pattern capable of recognizing the logical elegance that underlies all existence. The photons carrying starlight to your eyes have traveled at exactly the speed that cannot be measured, bearing messages from distant times and places while respecting the fundamental limit that ensures causality remains coherent across cosmic scales. The electromagnetic fields generating your thoughts operate according to the same unmeasurable principle that governs the expansion of space itself and the evolution of galactic structures. You exist within a reality where some of the most fundamental features cannot be measured because they define the very framework within which measurement becomes meaningful. The speed of light stands as a testament to the profound interconnectedness of all existence, the mathematical beauty underlying physical law, and the mysterious relationship between the structure of rational thought and the structure of physical reality. In recognizing why no one has measured the speed of light, we discover that the universe is even more elegant and mysterious than we had imagined. We learn that some truths are too fundamental to be discovered through measurement because they constitute the logical foundation upon which all discovery rests. We glimpse the beautiful paradox of existence itself, where unmeasurable principles give rise to a measurable world, where undefined constants define the framework of definition, where the unmeasurable speed of light illuminates the deepest structures of reality through its very resistance to measurement. Tonight, as you rest in the embrace of space-time itself, know that you are part of this cosmic mystery, this elegant dance between the measurable and unmeasurable, this profound story where consciousness emerges from the same logical structures it seeks to understand. The speed of light may forever remain beyond the reach of our measuring instruments, but it has revealed something infinitely more precious: the recognition that reality itself is far stranger, more beautiful, and more deeply interconnected than we ever dared imagine. And so we arrive at the end of our gentle journey through one of the most profound mysteries in all of physics. We began tonight with what seemed like a simple question about measuring a fundamental constant, and we've discovered something far more extraordinary. The impossibility of measuring the speed of light isn't a failure of human ingenuity or a limitation of our instruments. It's a revelation about the deepest structures of reality itself. We've seen how this unmeasurable constant emerges from the very fabric of space-time, how it serves as the cosmic speed limit that protects causality from paradox, how it defines the framework within which all measurement becomes possible. From Romer's observations of Jupiter's moons, to Einstein's revolutionary insights about space and time, from the Michelson-Morley experiment to the modern definition of the meter itself, we've traced humanity's gradual recognition that some truths are too fundamental to be measured. The speed of light stands as a monument to the elegant interconnectedness of existence. It reveals that the universe isn't just a collection of separate objects with measurable properties, but a coherent logical structure where the deepest features are relationships rather than things. Every photon reaching your eyes right now travels at this unmeasurable speed, carrying information across vast distances while respecting the fundamental limit that keeps reality logically consistent. What makes this story so beautiful is how it transforms our understanding of knowledge itself. Science isn't just about accumulating more precise measurements of pre-existing quantities. It's about discovering the logical relationships that connect different aspects of reality into a unified whole. The speed of light teaches us that some of the most important truths about existence are structural rather than empirical, definitional rather than discovered. As you settle into sleep tonight, remember that you're part of this cosmic structure. Every thought in your mind propagates through neural networks, at speeds ultimately governed by electromagnetic processes that unfold at light speed. The atoms in your body were forged in stellar cores through reactions that respect this unmeasurable constant. You are temporarily organized stardust, contemplating the logical principles that govern your own existence. The universe has evolved conscious beings capable of understanding why one of its most fundamental constants cannot be measured. In grasping this paradox, you touch something profound about the mathematical elegance underlying all phenomena. You participate in the cosmos, coming to know itself through the remarkable capacity for rational thought that has emerged from billions of years of cosmic evolution. The speed of light may resist all attempts at direct measurement, but it illuminates the deepest structures of reality through its very unmeasurability. It reminds us that mystery isn't the enemy of understanding, but its eternal companion, pointing us toward truths that transcend the traditional boundaries of measurement and definition. Tonight, as photons from countless stars converge on Earth at exactly the speed that defines space-time itself, you rest within the embrace of principles so fundamental they organize reality from quantum scales to cosmic horizons. The unmeasurable constant that governs light's journey through the void also governs the conscious experience through which you contemplate its nature. Until we meet again, remember that you're part of something magnificent and mysterious, a universe where unmeasurable constants create the very possibility of measurement, where undefined principles define the framework of definition, where the speed of light illuminates reality's deepest secrets through its beautiful resistance to direct observation. Sweet dreams, fellow travelers in this cosmic story that connects us all.